Hello and welcome to our first video on proton NMR basics. I put this formula for unsaturations here as an aside, so it's not really dealing with this, but in solving our problems, if you're given the molecular formula, which is usually from high-resolution mass spectrometry in conjunction with NMR, you will get the number of rings and or multiple bonds. So a double bond would be one unsaturation, a ring would be an unsaturation, a triple bond would be two unsaturations, a carbonyl would be an unsaturation. So as you're solving your practice problems, you're going to want to apply that to the formula. Now onward to proton NMR. Just some basics. The 400 megahertz instrument that we have can be scaled in two ways. The more typical parts per million, ppm, 0 to 10 units, or hertz values. So a 400 megahertz instrument is 4,000 hertz. And so the chemical shifts are typically reported in ppm because it's a useful quantity to remember. 9 ppm versus 3663 or something like that. So, but hertz values are still useful for measuring of coupling constants, which we're going to talk about a lot more about later. But say you had a doublet like this. The center of the doublet would be the chemical shift of that signal in ppm. The splitting is measured in hertz values like you see here, and I'll show you toward the end of this video how that's applied. Now, resolution increases with higher magnetic fields. So this is an extreme example comparing 200 megahertz and 500 megahertz for the molecule cholesterol. Pretty big molecule with a lot of overlapping signals, especially in this region, but you can see how much better it is at 500. Still not perfect though, right? You know, so a lot more has to be used to determine the structure of molecules like this, carbon NMR and 2D NMR. But still a dramatic improvement. And it makes sense because if you had a scale, say, from 0 to 4,000 hertz, like a 400 megahertz instrument, and you took it to 600 megahertz, you're spreading everything out the scale. So a doublet that originally is like this would look more like this at 600. So you can get resolution of overlapping signals if that's the problem, which it often is. We're going to focus on interpretation of NMR. And these four terms or concepts are the most important. Chemical shift we've already kind of discussed. Equivalence, in other words, which proton groups are equivalent to each other, which protons are in the same chemical environment. Same concepts go for carbon NMR. If they are all equivalent, they will integrate together into one signal, and that value of integration will tell you how many protons are represented by that signal. You want to figure all this stuff out before diving into the coupling or splitting. You definitely need to know equivalence before splitting. Okay, so the best way to look at equivalence is some examples. Are these two protons equivalent? So here we have all kinds of symmetry in the molecule. There's a plane of symmetry that contains the chlorines, and on either side of that plane are the two protons, so they are equivalent, yes. In fact, the same reasoning applies to here. The fluorine and the chlorine are in the same plane. The two protons are on either side of it, and so these are equivalent. When you're looking at equivalence, you want to see if there's ever a point of difference in terms of are these protons are in different chemical environments. The other thing that's important to remember is that there is free rotation around single bonds. Because of this rotation, these protons are always in the same chemical environment, and so they're equivalent. Now over here we have a molecule that has a lot of symmetry, but if we look at the different protons, here's a proton attached to a carbon that has a chlorine on it. Here's another one attached to a carbon with a chlorine on it. But these two over here are attached to carbons with fluorine on it. But the symmetry, if you look at it carefully, indicates that these two are equivalent and that these two are equivalent. Again, the next example really is the same argument with free rotation. These two are equivalent. Of course, an individual proton like this is unique and equivalent to itself. Same with that one, and same with these three. The three protons on a methyl are always equivalent. Equivalent to each other, equivalent to each other. All four of these are actually equivalent to each other as well, because these two groups are the same, and there's a plane of symmetry down the middle of the molecule. Not really drawing these planes perfectly, but with respect to if trying to find a point of difference attached to this carbonyl group on the other side, these on the next position, but in a plane, equidistant, and remember there's free rotation also. So those four are equivalent. These two are equivalent, clearly. Unique, unique. Finally, rings, it's important to recognize, create often inequivalence. Rings are locked, and so this ring has a phenyl group on the upper face, proton on the lower face. The whole ring is locked. It might flex a little bit, but the phenyl's always on top, the proton's always on the bottom. Therefore, the top face is a different chemical environment than the bottom face, and both protons here, while equivalent to each other, are different from these two protons here, which are equivalent to each other. So equivalent, equivalent, but these two are not equivalent. Okay, so lots of examples help see that. Any of these equivalent groups will integrate under one signal, and it'll tell you that that signal has 2 protons or 3 or 4 or whatever it is. Coupling and splitting. 2 main types of observed coupling in proton NMR. So what we see here is coupling, and coupling takes place through bonds, not through space. And what we see here is called vicinal coupling. That's the most common. But we do actually often see geminal coupling, where these protons are coupled through the same carbon that they're attached to. Often you see this in rings, where the top and bottom faces are inequivalent. There's a notation that we use for coupling constants. Technically speaking, it's a J value. You can read this pretty clearly for yourself. The notation is, this is the number of bonds apart, the coupling where it is that we're talking about, the atoms we're talking about, referring to, that are coupling each other. And as you see, coupling occurs between bonds. So this notation, coupling constant, 2 bonds apart, 2 protons, that's the same as our geminal coupling example up here. 1, 2 bonds. 3 bond coupling is like our vicinal, 1, 2, 3 bonds. Interestingly, and actually very importantly for later in the course, if you have an arrangement like this, for example, it's possible to have coupling between protons and carbons. That would be a J2CH coupling. Very valuable information for structure determination. There's also the phenomenon of long-range coupling. So long-range coupling depends on configuration, conformation, other things like conjugation, for example. So, but these two protons will show 4 bond coupling. 1, 2, 3, 4 bond coupling to each other. It'll be very weak coupling, most likely, due to the W shape, interestingly. So this might give an extra split. Okay, say if there was nothing else coupling these protons, you would get just a notch in the top probably for this long-range coupling. But the higher the field strength, the better you will see that. And sometimes it's useful in interpreting. Aromatic systems often have long-range coupling, actually. So orthocoupling, and I'm just going to do these arrows for convenience. It doesn't imply through space. About 8 Hertz splitting. So this proton would be a doublet with 8 Hertz coupling. This proton would have 8 Hertz coupling in return, but this is also coupled long range through the conjugated system, meta coupling, an additional 1 to 3 Hertz. So this proton here would appear as a doublet, further split very finely. Each peak of the doublet has an additional longer range split. So this is a doublet of doublets, DD. And then this one right here is only coupled meta, so this would just be a finely coupled doublet like that. In fact, though, sometimes we see 4 bonds all the way across para very weakly. Sometimes we see it, sometimes we don't. Okay. Just to get a better visual idea of what this looks like, so the top spectrum is in ppm. And so think about it. In your simple examples, you would have a pair of doublets, and you would know that those doublets are 2 protons coupled to each other. But what if you had a spectrum where there was like 6 different pairs of doublets? How do you know which pair of doublets is coupled to which? So the ppm values are not used for coupling. Notice the spectrometer gives you values for the tops, so you would have to take the middles of these for the ppm value, say, for that signal. Below is the same spectrum where I've calculated coupling constants in Hertz. So this was reprinted in Hertz values. And notice these 2 Hertz values match. While you can see a smaller value for the 2 finer splittings that are on this signal. The other signal in this portion of the spectrum that's split has completely different coupling constant values. So this tells us that these 2 signals are protons that are coupled to each other. And it does look like this one right here is further coupled long range to something else, kind of like the example I was showing you. And you can see the scale printed in Hertz down here. So that's an example. It's not just that you can determine what is coupled to what, but you can also determine geometry. And this was worked out by a scientist named Karplus, who won the Nobel Prize for all his work on NMR. But he came up with the Karplus curve. And notice what this is showing you is the angle between these vicinal protons, and the angle relates to the coupling constant J. So in theory, at 80 some degrees angle between this proton and this proton, there's zero coupling. While at 180 degrees, there's the largest coupling of about 10 hertz. So let's take the well-known example of a cyclohexane ring. You have axial and equatorial substituents. Maybe you're trying to figure out which of these protons is which in your spectrum. You can determine that what's coupled to what by coupling constants, but you can also use those values. So, for example, axial to axial coupling is predicted by the curve to be 180 degrees and 10 hertz, and the experimental value for cyclohexane is right in that range, the observed value. Axial to equatorial coupling value. The angle here is about 60 degrees if you build a model. At 60 degrees, the coupling constant should be about 1.8 theoretically. Observed, not too far off. And same with equatorial coupling. 60 degrees, 2 to 3 hertz. So the little differences in observed and experimental were actually refined by his later work, but this is still a pretty great approximation and can be cited in publications still to this day. So you're getting not only where the protons are connectivity-wise because they couple to each other, but also geometry information. All right, so on your own, I posted the chemical shift matching exercise on Canvas, and you could probably refer to the table of proton NMR values to help you on that. Eventually you won't need to. Keep working your practice problems, and I'll post the answers to those pretty soon. Tuesday's Zoom meeting will be hopefully mostly problem solving, like just working our way through one or two complete problems. And then look for more videos to come.